Okay, what did we have? We had the expectation of some function of x equals the integral from minus infinity to plus infinity, that's infinity, x equals that, of f of little x, where f is a function like x squared or something, times the probability density of x with respect to x. That's nice. That's very nice, isn't it? Okay, so now we're in a position to start thinking about moment generating functions. Okay, and this is defined as the expectation of a particular function of x, e to the tx, where t is just some variable, which is sort of fixed. It's fixed in a sort of in a peculiar kind of way. What I mean is that it's got a particular value, but once it's got that value, it sort of doesn't alter. It's not random. It's just a variable. It's a bit odd, really. Well, there it is. Well, look, that's it. This is the moment generating function. Let me write it out again. The expected value of e to the tx, e to the tx, like that, and that's called m sub x of t. So this thing here has got its t has got a particular value. I can shove any value I like for t in there, and here's a function of t, m sub x of t. Well, that's nice. Well, alright, let's have a think about this. Well, we know the formula for it now. The expected value of, from, where are we? From this formula here, that formula there, we just bung in f of x equals e to the tx. That's the function we're going to use. So the expected value of e to the tx is only equal to the integral from minus infinity to infinity of e to the tx p sub x of x dx. And we know all these things. T is the value. It's a bit mysterious. It's sort of, it's the argument of the function really, but it's sitting there. It's not random. It's just a value. This is integration over x, yeah, so we're happy with that. That's just the horizontal axis of this PDF, which I've lost. Well, wherever it is, it's up there somewhere. Okay. This is our probability. This bit here is the probability density function, dead easy, and x is just the variable we're integrating with respect to. Well, all right, that's great. Now what I'm going to do is do some stuff with it. What I'm going to do is take that exponential here, take that exponential there, and I'm just going to write it out. I'm sure you'll remember e to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus, and so on, plus x to the n over n factorial plus blah blah blah. Alright, so I'm just going to write that out. I mean, sometimes I'll use the notation like the sigma of a, oh no, it's not a, I can even rub it out, look. Oh no, I can't. Let's try that again. Stroke eraser. Sigma of x to the n over n factorial from n equals 0 to infinity. I just like writing it like that. So let's have a look at this. We are working out the moment generating function of m sub x of t equals the integral of e to the tx over the whole real line p sub x of x dx. And what's going to happen is once I've finished fooling around with this, what I'm going to do is put a particular form of my probability density function in. I might put a Gaussian in or some other kind of function I'm interested in. But for the moment, I'm just going to leave it free. I'm just going to write p sub x, and then I can substitute what I want in. And now I'm going to expand this. So it's the integral over x is a real number from the minus infinity to infinity of 1 plus tx plus tx squared over 2 factorial plus tx cubed over 3 factorial plus dot 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 times p sub x of x dx. How about that? Looks a bit bad like that, but there it is. I'm going to rewrite it in a slightly different way. I'm going to rewrite it like this. The integral over x is real 1 plus tx plus t squared x squared over 2 factorial plus t cubed x cubed over 3. I'm not doing anything clever here. All I'm doing is expanding these brackets out here. Times my probability density x dx. Alright, and that is my moment generating function of t. Now what I want to do is this. I want to use that same... I'm just going to... It's a bit cheeky really, but what I'm going to do is differentiate. I'm going to differentiate with respect to t. I'm just going to think about that. I'm just going to differentiate it, and I want you to think back to the first screencast. So what I'm going to do is I'm just going to differentiate it once. I'm going to say d by dt, just differentiate it once. I'm going to differentiate more than once, and some of you, while you're thinking, are going to think, what's going to happen to these powers here? I'm going to differentiate with respect to t, my moment generating function of t, equals, well, let's have a think about it. When you look at this great big mess here, where are the t's? There's one there, one there, one there, one there, one there. There's no t in this bit. There's no t in this bit, so that doesn't change. It's the integral of, well, differential of 1 is just 0, isn't it? So it's x plus, what's this one? That's going to be t times x squared plus, what's this one? That's going to be t squared x cubed over 2 factorial plus dot dot dot, and all of that times p sub x of x dx. Sweet. Well, that's great, isn't it? But what I'm going to do now is evaluate this at t equals 0, just because I can. Well, not just because I can actually, because it makes all this rubbish disappear. Look, I can forget that. There's a t there, so when I put t equals 0 in, that drops out, and that drops out, and all the other terms, all these dot dot dots drop out. So let's have a look at that. That's equal to the integral of x plus nothing, because all the other terms in this bracket have vanished. P sub x of little x dx, which equals, oh look, the expectation of x. That's nice. Let's go through that again. I've got m sub x of t, I've differentiated it, and I've set, and now I'm evaluating this moment generating function at t equals 0. And we get this, which is the expectation of x. So wrapping it all up, d by dt of the moment generating function of x, which is a function of t, evaluated at t equals 0, equals the expectation of x. How about that? How about that? Isn't that neat? I think so.